Welcome back, explorers. In this video, I want to visualize how interpolation works. These type of calculations are usually used to kind of fill in the gaps when there are not enough pixels available for what needs to be shown. And I'm going to start out with a wave pattern using the distance from the center, and that looks like this. And I'm also going to use a charted one-dimensional version of waves so that we can visualize what that looks like as we apply some of these interpolation functions. And that looks like this. And so for the first interpolation that I'm going to call this function that I've named integer interpolate alias. There's quite a bit there, but this will calculate aliased interpolation between pixels. The integer part of the name describes how the number of pixels is being reduced. Since all of these images are being generated by math, there's no limit to the resolution or number of pixels, so we have to artificially limit it by rounding to the nearest whole number in the calculation. So that's what the integer is for. And if we look at the image for that, we can see that we have some really huge pixels. So in the next one, I'm actually going to do a little trick here where I first scale it up times 10 and then scale it back down to a tenth so that we can adjust the size of our pixels. And here's the image for that. And you can see that the alias method doesn't actually do anything to gracefully fill in the gaps. This method is sometimes called nearest neighbor or an interpolation type of none. It doesn't actually calculate anything other than what the nearest value is. And if we look at a charted version of that, here's what that looks like. And then we're going to move on to a different type of interpolation. Now that we've kind of seen that we're creating these large pixels, we're going to apply linear interpolation now in this case. And if we look at what linear interpolation looks like applied to those waves, it looks like this. So here's the original, and here's with linear interpolation applied. Now, linear interpolation, it uses a technique of kind of forming a line from the last value to the next value and working its way up or down that line. Now, it might even be easier to see when we chart this value out. So if we look at the original chart of the waves, and then we look at the linear interpolation of that, it looks like this. Well, actually, these are the values that the interpolation sees, and then when it does linear interpolation, it blends between them with straight lines. And I have another type of interpolation that I'll just cover here. It's similar to linear interpolation, only it uses a slightly different technique to blend between them. And that actually, it blends using a sine wave instead of a line. And if we compare, here's what linear interpolation looks like. It kind of has a little bit of a star peak at the center, and here's sine interpolation. Neither of them look really great, but they each kind of have their own visual artifacts. And if we do actually have a charted version of the sine interpolation, and that looks like this. And you can kind of see the slight waviness to the interpolation there. So we go from the full aliased version of the data to these kind of blended curves between the points, which linear interpolation seems to be more accurate here, but the sine interpolation just kind of uses a different technique. And then the last type of interpolation that I want to show is called cubic interpolation. And that actually looks like this. Now, if we compare this, here's what the linear interpolation looks like. And we can see that the cubic interpolation actually looks quite a bit better. Cubic is the smartest of these calculations because it looks at even more values and finds a smooth curve that connects the points. We also have a charted version of that to look at, and what's interesting is the charted version looks like the original value of the wave. If I load up the original wave, I can't even tell the difference between the two. So Cubic does a really good job of of fitting the data to the appropriate curve. And for the intro animation, I actually just used these same wave patterns, but I adjusted the scale so that the waves were smaller than the pixels. And this causes the pattern of the waves to line up with the grid pattern of the pixels in some pretty interesting ways. This is known as the Moiré effect. There are a couple of links in the description if you're interested in learning more about some of these topics. But thank you for watching, and come explore with me again.